Have you ever wondered what lies at the heart of all matter? What powers the sun, lights up cities, treats deadly diseases, and yet holds the capacity to destroy civilizations? The answer lies not in the vastness of space, but deep within the atom. Welcome to Inside the Atom, the power and peril of radioactivity. This is Episode 1, Unveiling the Atom, the birth of nuclear chemistry. Long before science had tools or equations, ancient Greek philosophers imagined that everything was made of tiny particles. Around 400 BC, Democritus proposed the concept of atomos, meaning uncuttable. The idea was dismissed for centuries. But in the 19th century, science returned to the atom with curiosity and began to uncover something far more powerful than anyone had imagined. Unlike traditional chemistry, which focuses on atoms and molecules interacting through their electrons, nuclear chemistry dives deep into the core of the nucleus, where protons and neutrons live. When the nucleus changes through fusion, fission, or decay, it releases energy far greater than ordinary chemical reactions. That energy can heal, destroy, or power the world. In 1896, a French physicist named Henri Becquerel was exploring how certain minerals responded to sunlight. He stored photographic plates with uranium salts expecting to return later and expose them to sunlight. But when he developed the plates early, he found them already imprinted. The uranium had emitted some kind of invisible energy without any help from the sun. It was a complete accident, and it changed history. That energy came from within the atom itself. It was a new phenomenon, radioactivity. Marie and Pierre Curie took Becquerel's discovery and pushed it further. They discovered two new radioactive elements, polonium and radium. Marie Curie, who later won 2 Nobel Prizes, gave the phenomenon its name, radioactivity. Her work helped define the field of nuclear chemistry and revealed the dangers and promise of invisible energy. But what were these strange radioactive emissions? Scientists identified 3 types: alpha particles, beta particles, and gamma rays. Alpha particles are heavy and positively charged. They can't even pass through paper but are hazardous if inhaled. Beta particles are lighter, like high-speed electrons or positrons. They can penetrate skin but are blocked by aluminum. Gamma rays are not particles at all, but electromagnetic radiation, extremely powerful, extremely dangerous, and requiring thick shielding to stop. This changed the fundamental belief about atoms. They weren't indivisible. They could decay. They could transform, changing from one element to another. That was unthinkable before. The atom was no longer the smallest and breakable unit. It was dynamic. It was powerful. To understand how radioactivity worked, scientists had to understand the structure of the atom itself. In 1897, J.J. Thomson discovered the electron, proving that atoms had internal components. He imagined the atom as a plum pudding, with electrons like raisins scattered in a positively charged dough. But in 1911, Ernest Rutherford conducted an experiment that shattered that model. He fired alpha particles at a thin sheet of gold foil. Most passed through, but some bounced back. That could only mean one thing: atoms were mostly empty space with a dense, positively charged core, the nucleus. This was the beginning of the nuclear model of the atom. Later, scientists discovered the proton and the neutron, the building blocks of the nucleus. The neutron, discovered by James Chadwick in 1932, was especially important because it made nuclear reactions possible without repelling other particles, since neutrons carry no charge. This allowed scientists to trigger chain reactions, laying the groundwork for nuclear fission. Here's a staggering idea. The nucleus is only a trillionth the size of the atom, but holds almost all its mass. Inside that microscopic core, protons' positive charges should repel each other, but they don't, thanks to the strong nuclear force. It's the most powerful force in nature, billions of times stronger than gravity. Without it, atoms and the universe wouldn't exist. But disturb that balance, and the results are dramatic. When a nucleus becomes unstable, it decays. When two light nuclei fuse, energy is released. When a heavy nucleus splits apart fission, it can unleash enormous power. By the early 20th century, scientists were unlocking new atomic behaviors. They discovered isotopes variants of the same element with different numbers of neutrons. They observed transmutation, where one element changed into another, and they developed the concept of half-life, the time it takes for half a sample of a radioactive element to decay. Some half-lives last fractions of a second, others billions of years. These discoveries weren't just scientific milestones, they were the beginning of new industries and global change. Medical imaging and cancer treatments, nuclear power plants, atomic bombs, environmental tracing, deep space travel, agriculture, forensics, archaeology. The atom had gone from abstract idea to world-changing reality. And yet, with every new revelation, humanity faced a deeper dilemma: could we control the forces we were unlocking? By the mid-20th century, the dual nature of nuclear chemistry became painfully clear. On one hand, radiation could destroy tumors, power cities, and reveal the Earth's ancient secrets. On the other, it could vaporize cities, poison environments, and leave radioactive scars that last for millennia. The atomic age had begun, and it was as much an ethical revolution as it was a scientific one. In future episodes, we'll explore the lives of the pioneers who made these discoveries, the science behind nuclear reactors and weapons, and how radioactivity continues to shape medicine, space exploration, and geopolitics. For now, we leave you with this: the atom, once a philosophical idea, became the most consequential scientific discovery of the modern world. We are only beginning to understand its potential and its price. This is Inside the Atom, and you've just seen Episode 1, Unveiling the Atom.